Okay, thank you very much. Thank you for inviting me to speak in the UK again. I'm happy to be in the UK for the first time since, well, at least 6 years or something. I will talk about my joint work with Weronika and Łucja. And this is work that we are still writing up, and some details can be incorrect, so sorry for that, but I think that most of the stuff is well checked. So I will start on some very easy stuff. I will be talking about the projective scheme or variety in some examples over an algebraically closed field, and L will always be a line bundle on X. By phi L, I will denote the natural map determined by sections of L. And I will, the classical definitions of variableness and ampleness are on the slide right now. Just to be very formal, I will repeat them now. This is just to say that L is very ample if two conditions happen. First of all, the map defined by sections is regular and it is an embedding. And second of all, the pullback of the O of 1 on the projective space is exactly L. It's not something else than L, but exactly L. And then of course, the bundle is ample if some of its powers is ample. So there's a bunch of things that you certainly know about ampleness. So for example, if you have two very ample line bundles, L and L prime, then their tensor product is also very ample. And you have certainly seen the proof of that, but just to briefly recall it, it relies on the following diagram that will be useful also in much more complicated setting at the end of the talk. So this follows from two embeddings, diagonal and square embedding. So first, diagonal embedding is the standard embedding of X into the product of X times X, and then you embed each factor using the map corresponding to each of the line bundles. And after that, you take the Segre product of these two, and it turns out that this is the same if you go the other way around. There's using the product line bundle and also a linear embedding of this space of sections into this tensor product. Well, it doesn't have to be an embedding, but in this case it is. Typically is. And then this is the classical way of proving this, and this diagram will come back at the end of the talk again. So, okay, so the product of two very ample line bundles is very ample. Of course, product of two ample line bundles is ample again. And also the very ample times ample is ample by the previous items. But the question that I want to ask you is, if you have a very ample and ample, and take their product, doesn't necessarily have to be very ample. So it turns out that the answer is negative. And here is an example that I wrote in my handwriting. So if you take a genus 3 curve, this is a curve containing a projective plane. And this equation is very explicit, so I will probably be careful about characteristic 2, maybe 3. Maybe this should be slightly different equation in low characteristic, but let's just assume we are working over characteristic 0. So this is a smooth curve of genus 3, and this point P, which has coordinates 0, 0, 1, is a point on this curve. And moreover, if we take a hyperplane section, y equals 0, then this curve C intersected with equation y equals 0 is a divisor which is equal to 4 times point p. This is because if we take y equals 0, then these two terms vanish, we get only x to the 4. So this means that 4p is very ample. Well, the divisor for the line bundle corresponding to the divisor of 4p is very ample. Therefore, p is ample. But it turns out that 4p plus p, so a very ample plus ample, which is 5p, is not very ample anymore. And this is summarized on this next slide. If we consider a smooth, well, this is well, in this case, this 5p is not very ample, and to see this, well, we have to use Riemann-Roch to find out that the space of sections of 4p has the same dimension as the space of sections of 5p, and obviously we have the product of, well, we can take the 4p and always add one section vanishing, multiply this by section vanishing at p, and we get the we always get this inclusion, and the dimension count shows that these two spaces must be equal. Therefore, all sections vanishing at p with multiplicity 5, sorry, all sections of this line bundle of 5p is necessarily must vanish at point p with multiplicity at least 1. So we get that 4p is very ample. Well, clearly the 8p would be very ample, and we have that this is the 5p is not very ample, and also it turns out that these guys are not very ample either. Also not very ample is the 6th power of the line bundle, but the 7th power is very ample, and all the further powers are also very ample. So this is what happens in general. That's an example of a general phenomena. That there will be a starting point. In this case, this is the 7th power of L, of a line bundle L, such that everyone from here onwards will be very ample. And that's this is the kind of phenomena I'm going to talk about. But it's not true that if we have started, well, this is the special power, which is very ample, but there are some guys in between which are not very ample. And I want to talk about this kind of phenomena. Okay, so this is the summary of what I taught in the previous slide. So we have, this is a general theorem for any scheme X. If L is ample, then L to the power m is very ample for all sufficiently large powers of M. So it cannot happen that every second power is ample and every second power is not ample. Let me stress that I'm talking about line bundles, so Cartier divisors. Obviously, if we add Q Cartier divisors, then this is not true anymore. And this statement follows, well, in some not very immediate way from Serre's vanishing theorem, and I will come back to this theorem a little bit in a couple of pages. Okay, so so we discussed the powers of a fixed ample line bundle, but the Picard group, the group of all line bundles, can have more dimensions and more complicated structure in general. I'm considering any schemes at this moment, any projective schemes at least. So what happens is that there is this, for projective scheme there is always this ample cone, And this is like a very simplified picture here. This is a case where the Picard group is just a two-dimensional integer group. But of course, there could be also continuous parts of this. There could be also much more dimensions and so on. But in general, we have this ample cone, which is in some sense an open cone, at least in this Picard group tensors with real numbers. And what happens is that we have inside this ample cone, we have the set of very ample line bundles, and there might be some sporadic cases like these two dots here, but apart from that, it will turn out that there is like a full cone where everyone in this region is very ample. So in other words, there exists a line bundle L, the starting line bundle, such that for all the any ample line bundle L prime, the product of L times L prime is very ample. So here this will be something like this line bundle, and then everyone in this cone is very ample. And this is exactly the topic of my talk. I want to say this, repeat this again. I will say that the property of line bundles on X is satisfied for sufficiently ample line bundles if there is a starting line bundle like this L0 here, such that for any ample line bundle L, the product L0 times L satisfies the property P. So I'm not assuming that no one outside this region satisfies. There might be sporadic cases which work fine, but I'm looking for properties which are satisfied by a pretty large subset of ample line bundles. And this ample can be equivalently well said to be NEF, but I don't want to go into the definition of NEF, so I just stick to the ample definition. Well, let me stress that in this talk today, I'm not really interested in in efficient ways of choosing L0, choosing this starting line bundle L0. So I don't really care if I chose this one or a little further down into the cone. This is perfectly, either of those is perfectly fine for me. So NEF or ample is no difference here. Okay, so the grandfather of all those properties that are satisfied for sufficiently ample line bundles is the Fujita vanishing. And you probably more often hear about Serre vanishing, which is slightly simpler to state. And it says that for any ample line bundle and n sufficiently large, and for any I, we have vanishing of all these cohomology groups. So if we have ample and you take the very large power of this ample, then this will only have H0, no H1, H2, and so on. Fujita vanishing is similar, but it says about sufficiently ample line bundles. So it just says that for a sufficiently ample line bundle and any I, at least one, we have vanishing of H1. Oh, sorry, this F is just any coherent sheet. I just should have stressed that. Hi of F tensor L is 0. And let me recall once more that this, without using this definition, the definition of this sufficiently ample, this means that there exists a starting line bundle L0, such that for any L, which is equal to L0 plus ample, the higher cohomologies of this F tensor L vanish. And there are also relative versions of these theorems. or both of them. I perhaps don't necessarily want to state them right now, but maybe, well, okay, let me go quickly through the relative versions, but this is not so important. In the full generality, it's not so important, but the cases that I will be using in this work are the following. We have two, well, the relative Fujita vanishing and relative Serre vanishing are much more general than that, but let me just state this version here, simplified version. So we have X and Y, two projective varieties, have a coherent sheaf on the product, which is flat over Y. So we think of it as a family of sheaves on X. So family in the sense that it changes in a flat way. And then for a sufficiently ample line bundle on X, and any Y, any point Y in Y, the cohomologies vanish. All the higher cohomologies vanish for any Fy. So we have Fy is just the restriction of the sheaf F to the fiber over Y. So we have this family of sheaves, and we can simultaneously take this L, this family of L's that vanish that have vanishing cohomologies. Okay, so let me give you a quick example how to prove that using relative Fujita vanishing, how to prove, or at least sketch the proof that sufficiently ample line bundle is very ample. So that's it that we started the discussion in the beginning. So we have as Y, we take the Hilbert scheme of 2 points on X. This guy here. So as a set, this consists of just 2 points. Each point in Y either represents 2 points on X, or represents a point with a Zariski tangent direction to this point. And then we can take the universal ideal sheaf inside the product, and inside of the structure sheaf of the product. And it turns out that by Fujita vanishing, H1 of these things, these two things vanish. And therefore, this is very similar to well, if you have ever seen the criterion for ampleness in Hartshaw's book, then this is exactly this condition that the appropriate maps of sections are surjective of the section from L to the L restricted to either 2 points or L restricted to a tangent direction. We must be, the section maps must be surjective for each pair of points. And this is guaranteed by vanishing of this cohomology group. Therefore, this concludes the sketch of proof of the fact that sufficiently ample line bundle is very ample. Okay, so we have this example of properties of sufficiently ample line bundles. So very ampleness, great. Also, what happens is that if we, at least for if X is normal variety, then the embedding of X into the projective space determined by sufficiently ample line bundle is projectively normal. Maybe I will have time to come back to this property later on. This, well, if X is normal variety, this is equivalent. The projective normality is just equivalent to the fact that the affine cone over X over this embedding is normal. It's a normal variety. It's also equivalent in the to the more algebraic expression that some appropriate algebra of sections is generated in degree 1, and this is actually how we prove this example. And in fact, this doesn't really use normality. So there is this weaker property than projective normality, which by some authors is also called projective normality. And this weaker property can be proven without assuming that X is a normal variety. It works for any scheme, actually, projective scheme. Okay, and then a theorem that I want to talk about a little bit in more details is that if you have an embedding, we already know this is actually an embedding by sufficiently underlying bundle L. Its ideal the ideal of X in this embedding is generated by 2 by 2 minors of a matrix with linear entries. And this is, I have the picture, not yet. Yes, I have the picture. So this is the diagram that we have seen at the beginning as an argument for the fact that the product of two variable is variable. So here, we use this diagram to produce the matrix that gives us the minors, right? In the above thing, we have this matrix with linear entries. So I want to explain where does this matrix come from. So for this, we need 2 line bundles, and we express L as a product of these 2 line bundles. So it will be a product of L and the rest that needs to be taken. So what we need is that both M and the remainder are sufficiently ample. So there will be some region where M can be, there will be some other region where the remainder can be, and the L should be at least anything from the product of these 2 cones. And then once we have this diagram, which is the same diagram we used to prove the Serre, the product of 2 ample line bundles is 2 variable line bundles is variable, is now has this linear embedding here, which is in this setting it's always a linear embedding, and this embeds the space. Well, there is this natural matrix here coming from the structure of tensor product, which we can pull back to the smaller projective space here, and this produces a matrix with linear entries. That's exactly the matrix appearing in the theorem of Jessica Sidman and Greg Smith. So these kind of expressions appear a lot in practice. So we will learn about some Veronese varieties or Serre varieties, or maybe some scrolls. Then very often the easiest way to describe embeddings of scrolls is as a set of points where some rank of some matrix is at most 1. Right? So this is something that we very often write. And then this matrix will have, well, in nice cases it will have linear entries, sometimes it will have not linear entries, but in this case we always have linear entries. So these are, in particular, these defining equations of x in this setting are quadrics or quadrics. The ideal is generated by quadrics. And what happens? Well, I want to talk about secant varieties in a minute. So before going into secant variety, let me stress an important property of a matrix with linear entries. So if we have such a matrix, and we know that this matrix vanishes on our variety x, then if we pick 2 points on x and draw a line from one to the other, then since our matrix M, this is matrix M, has rank 1 here, rank 1, well, at most 1, on the blue points, on any point on this line, it will have rank at most 2. In other words, we have these 2 blue points here, 1 and 2. This is the matrix has rank 1 at each of these points, and any linear combination of these 2 points, which is any point on this projective line, the matrix will be also a linear combination because it has linear entries. So it has rank at most 2. A linear combination of 2 matrices of rank at most 1 has rank at most 2, and so on. So this is a conjecture that was first phrased for curves by Eisenbud-Koh-Stillman in the 80s, and then by Greg and Jessica in the same paper as before. I think it's 2011, published in 2011. So this conjecture is phrased as, well, here x should be a variety. X is variety. Projective variety, of course. So for any fixed integer r, the r secant variety to the embedding of x by a sufficiently ample line bundle as the ideal generated by the minors of a matrix with linear entries, and then this number, this size of minors is determined by this property above, right? I just treated the case r equal 2, but this generalizes to any number of points. And let me just state the definition of the secant variety. It's the secant variety is the union, the closure of the union of all linear spans. This is linear span of finite smooth subschemes of length at most r inside x. So we have this case here. This is one degree smooth degree 2 subscheme of x. So it consists of P1 and P2, and the linear span of P1, P2 is this red line here. The linear span in the projective space. So this is one of the linear spans that come up in the secant variety. Now we move points P1 and P2, and what we get is second secant variety of x. And if we want the r secant variety of x, then we just take higher, more points, and take linear spans of more points. So this is the conjecture that was phrased between 80s and 10 years ago. And here are some counterexamples to this conjectures. Well, so at least kind of counterexamples. So first of all, it's not going to be work out if we allow singularities to arbitrarily that singularities to live in our varieties. So for example, already for singular curves, badly singular curves, there is no chance for the conjecture to be true. So badly singular, well, maybe I'll come back to this later, but this is, for example, like already a curve which has singularities, well, which has like self-intersection but many times, and moreover, this is not supposed to be planar. Then this is going to be a counterexample, and then also, well, the conjecture does, well, at least some versions of the conjecture does not specify where these minors should come from. But if we assume that they come from, well, there is essentially only one way to produce them. We don't really know any other way than this using line bundles as before. So we're using exactly this method. So if we assume that they are supposed to come from this precise method, then also for R at least 14 and N at least 6, the conjecture fails for projective space, already for projective space. So the simplest possible variety you can imagine of 5 dimensions at least. So here's the modified conjecture that's also been considered and hinted at even by the authors of the previous conjecture. So instead of secant variety, we should consider something which is called Cactus Variety, and the rest remains the same. So we have fixed R, and we take the R Cactus Variety to this sufficiently ample embedding of X. And we expect that this guy has ideal generated by R plus 1 minors of a matrix with linear entries. And this Cactus Variety, well, remember we had this, so for secant variety, we have exactly the same thing, but we have added smooth here. But the Cactus Variety uses all possible finite subschemes of length at most R. Therefore, at some point, we will, well, for very large values of R, we will arrive at some schemes which are non-smoothable. And this is exactly this. For example, if X is smooth, and the dimension X is at least 6 and R is at least 14, then there will be some non-smoothable Gorenstein subschemes, and this Gorenstein condition is also important. I don't really want to go into the details why, but the main point is that this linear span will be significant. We always have secant contained in the cactus, and in some small values, if R is small, then there will be equality. But for large values of R and large dimensions, there will be strict inclusion between these two varieties. Well, okay, this is an honest variety. This is typically not irreducible, so it will be reducible, and that's a little technical problem. But the point is that we would like to control secant varieties, but at least in this conjecture we can control the Cactus variety, at least to some extent. Well, I should say that this it's well known, or by now it has been at least 10 years since the conjecture was phrased, I'll do more than that. But by now we know that essentially always whenever you have equations in the form of minors of the matrix with linear entries, then the Cactus variety will be contained in this rank condition. So this, if you want to produce the equations for secant varieties, well, you should always first check if they are not satisfied by everyone in the Cactus variety, just to be on the safe side. And this is the case. This is how the counterexamples are produced for this original version of the conjecture. Okay, so we don't know the full answer to if the full conjecture is true. We expect it's actually not true in the ideal theoretic setting, but we can prove it in the set theoretic setting so far. So the theorem says that we fix a projective variety and we fix an integer, a positive integer. Then the R Cactus variety of the embedding of X via a sufficiently ample line bundle L is set theoretically defined by the minors of a matrix with linear entries, and this is the same matrix as before in the theorem of Greg, Smith, and Jessica Sidman. And I should mention that with Farnik and Eshlo, I work on the generalization of this to scheme theoretic setting and the ideal theoretic as well. But then this is not going to be a variety anymore. It's going to have scheme structure. It's at this moment, I guess it's fairly clear that the scheme structure will be relevant, and therefore it will produce even further counterexamples to the ideal theoretic conjecture. Okay, what I'm left with is some basic ideas about the proof of this theorem, and for this I need to come back to the projective normality that I mentioned at the beginning. So I have, so what does it mean that what is this projective normality in terms of cohomological names? So we construct the algebra SL, which is the direct sum of H0 of XL to some power m for natural numbers, so maybe just to be on the safe side in case the positive integers or non-negative integers, sorry. And in this algebra, so X, we will say that X is projectively normal, or weakly projectively normal. If and only if SL is generated by the H0 of XL, so by the first gradient. And this is equivalent, so if, side remark, if X is normal, then this is weakly projectively normal. Isn't equivalent to projectively normal. Okay, and then this is the same. Well, so how can I prove using cohomological methods that this actually is? So what do I need to prove? To this I need to prove the surjectivity. It's enough to show that for all m, at least one. We have X, L, tensor X, sections of XL minus 1 is surjective onto this space of sections. And well, this comes from, again, vanishing, of Fujita vanishing, if L is sufficiently ample. I will come back to this in a more general setting in a moment. But before that, I want to discuss a product, X times X. And well, and there on the X times X, I have line bundles, which I will denote by L1 square product L2, which is just the pullback of the first projection of L1 times pullback of the second projection of L2. I have L1 and L1 and L2 are the line bundles on X. So what I want to say is that this is a class of bundles on X, and these are on X times X. And these are, well, not necessarily, these are all possible line bundles on X, but there is some class of those. And if we have P a property of line bundles on the product, which is satisfied by sufficiently ample line bundles, on X times X, then if L1 and L2 are sufficiently ample line bundles on X, let's say some more space. If I have two sufficiently ample line bundles on X, then L1 times L2 satisfies P. Well, I'm not sure if I want to explain this in details at this moment. By the way, I should stop at 10 to 11, 10 to 11, or just at 11 sharp?
You can take up to the full hour if you want to.
That's up to you, if how long you want to sit in front of the computer. Okay, anyway, the point is that if we have this, well, the ample cone is an open cone inside the Picard group of X times X. The Picard group of X times X it contains the Picard group of X square product X. But, well, not necessarily it's equal, but it will always be contained. And if we have an ample cone here, it will intersect this. It will intersect. There will be non-empty intersection with this lattice here, pullback, and then because the pullback of an ample from x 10 times the pullback of an ample from the other coordinate of x is ample, so the intersection is non-empty, and therefore this is an open cone here. Open cone in this Picard lattice. Of course, everything after tensorizing with real numbers. And then from this we can conclude the property. So using this, instead of proving a regular projective normality, would rather prove something which we call double projective normality. So we take two line bundles L1 and L2 on X. And we say that this pair L1, L2 is double projectively normal if the algebra is double graded algebra is generated in degrees 1, 0 and 0, 1. So in other words, by h0 of x L1 plus h0 of x L2. And it turns out that, again, sufficiently normal, sufficiently ample line bundles, if L1 and L2 are sufficiently ample, then the Fujita vanishing for the sheaf I delta inside the OX times X implies that if L1 and L2 are sufficiently ample, then the pair is double projectively normal. So this L1 L2 is generated by 1, 0, 0, 1 grading. This comes from this previous description of sufficiently ample line bundles, and it actually, well, it's a little bit too complicated, but this implies the regular projective normality. So it's not very direct way of doing this, but it's some way of proving this. And from this point, the idea of the proof is that if we have, so I should state maybe the just main idea and finish. The thing to do is if we have this phi L of x inside this projective space, large projective space of sections of L then the fact that our Cactus variety is contained in the set of R, well, the vanishing set, the set of points B such that the rank of appropriate matrix is at most R. This is the easier part. And it's actually always true whatever sensible matrix you put in here. But the difficult part is to choose the correct matrix and show the other inclusion, the opposite inclusion. This is easier and difficult. Maybe just a quick review. How do we construct this? So what we want, we want two line bundles L1 and L2, such that they are very ample. And double projectively normal. And once we have this, we want to write L as a product of L1, this to power 4 times R minus 1 tensor L2. A little bit complicated, but we want to construct this algebra as L1, L2, and we want the sections of L to be the degree, very specific degree in this algebra L1, L2. And from this point onwards, maybe this is a good moment to stop, but this algebra is useful to well, it has sufficiently large power of the single line bundle one, so that we can use just the regular graded algebra well, without worrying too much about the second grading on one hand, and the other hand, this allows us to present L in some very well, very structured way inside this algebra. So this one here is kind of remainder of what's left between, because we don't know if L is divisible by anything, but we can write, since L is sufficiently ample, we can write it as a sum of a large number of copies of L1 and one line bundle, which is the kind of remainder of whatever else is there. Okay, I think I will stop here. Just a good moment to stop. I don't want to start any deeper in the proof, that you're not going to sleep fast.